Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this next section of the course, we are going to study yet another famous deep reinforcement learning algorithm known as A3C. A3C stands for Asynchronous Advantage Actor Critic. As you can see, this term has 3 A's in it and 1 C, hence the abbreviation A3C. What's pretty nice is we've already done most of the groundwork for this algorithm. In fact, there's nothing new in terms of theory that we have to discuss. In particular, we've covered everything you need to know already in the section on policy gradients. As you may recall, the final form of the policy gradient algorithm we used was called actor critic, where the actor was a neural network that parameterized the policy, and the critic was another neural network that parameterized the value function. As you may recall, the advantage is just the term we use to measure the difference between the actual return at state S and the value at state S. In other words, it's how much better the action we took is relative to what we currently believe the value is. So now we know where the terms advantage and actor critic come from. First, let's review more closely how policy gradients work. As you recall, we're going to have two neural networks, the policy network and the value network. We can imagine that the policy network outputs pi, the policy, and the value network outputs v, the value. These networks have the weights theta p and theta v, respectively. The objective for the policy is derived by sort of working backwards from the actual policy gradient itself, or in other words, taking the integral of the gradient. This is just the return g minus v of s multiplied by the log of pi. Notice I've represented it as the loss here, or in other words, something to minimize rather than maximize, since that's what we'll be using in TensorFlow. On the other hand, the value network loss is simpler. It's just the squared error between the return and the predicted value. Then during training, all we need to do is loop through each step of the game, sample an action, and then update the weights of both neural networks as we can see in this pseudocode. So the pseudocode is as follows. While we are not done, we sample an action from the policy network. We get A. Then we perform the action A in the environment and we get S prime and R. We set G equal to R plus gamma times V of S. We calculate the policy loss and the value loss. Finally, we perform gradient descent to update theta p and theta v. One minor difference between this and A3C is that we're going to take n steps at a time, which means we can use the n-step return rather than the TD return. So here we see another opportunity to combine the different things we've learned in this course previously. Another minor difference is that we are going to regularize the policy loss by adding the entropy as a regularization term. If you recall, the entropy of a distribution is the sum over all events of the probability of the event multiplied by the log probability of the event. In our case, the k's just represent the different actions, and pi of k is just the probability of that action at the output of the policy network. In the end, we take the usual policy gradient loss and add the entropy multiplied by a regularization constant, which controls the strength of the regularization term. In practice, what this does is it encourages exploration. If you recall, entropy is somewhat like variance in that it measures the spread of a distribution. We get the maximum entropy when each event has equal probability, and we get zero entropy when all the probability goes to a single event, or in other words, the outcome is deterministic. So using entropy as a regularization term allows us to fight between those two extremes. One extreme being that all actions are equally probable, and the other extreme being that only a single action can ever be chosen for a given input state. Another big improvement with this algorithm is that we'll now be able to incorporate neural networks as our function approximator. Specifically, we'll be using convolutional neural networks, just like we did for deep Q learning, to process the frames of the screen of an Atari game as input. One thing to note is that for vanilla policy gradients, this approach didn't seem to work. You'll see that with A3C, we are now able to use neural networks, and later in this lecture, we'll explain why that's the case. So what makes A3C interesting is that it's asynchronous. In other words, what it does is take the algorithm we had before, but make it so that it's an asynchronous algorithm. In the rest of this lecture, I'm going to explain to you exactly what that means. First, in modern computing, what we often like to do is run things in parallel. So for example, suppose I had a for loop over 1 million files that I need to do some processing on. Well, in code, this is very simple. I can just loop over all 1 million files and run my function on each file. But this process is slow. If I have 2 million files, the time it takes for this code to run just doubled. So what can I do? These days, a popular method is to use multiple machines. So I can have 1,000 CPU cores, each responsible for 1,000 different files. In this way, I've reduced my computation time by a factor of 1,000, minus any overhead for coordinating each worker machine. But we don't even have to go that far. As you might already know, your computer, if it's reasonably modern, already has multiple cores which can run code in parallel. So while you might only have one machine, you can still take advantage of the multiple cores that exist inside it. So what is the basic algorithm for A3C? Conceptually, we're going to have one set of master networks, one for the policy and one for the value function. You can think of that as a set of global networks. Now, every so often, this global network is going to send its weights to a set of worker machines, each with their own copy of the policy network and the value network. Then, each of these worker machines is going to play a few episodes of the environment using its current network weights. From its own experience, each worker can also calculate the policy gradient updates, as well as the value function updates. Now, of course, keep in mind that only this worker knows about its own updates. Finally, the worker sends its gradients to the global networks so that the global network can update its parameters. And every so often, the global network gives its new updated parameters back to its worker machines. So worker networks are always working with a relatively recent copy of the global network. So why is this good? Well, firstly, now the global master network has no work to do. It's not going to be involved in actually playing the environment. Only the workers do that. So the workers, hence their name, are doing all the work. They play the episode, calculate the errors, and find the update gradients. The global master network is the beneficiary of these updates. And of course, since the global master network has multiple workers playing episodes, it can gather a lot more experience in parallel than it could have by playing the environment by itself. Long story short, we save time. But there's another big advantage to doing things this way. Remember that there's always some randomness in each game. Each game isn't going to start the same way, and each action sampled from a probabilistic policy will vary. So every game that the workers play is going to be different. If you recall, sometimes in reinforcement learning, the performance of our agent can drop off sharply due to a bad update. By having multiple workers contribute to the global master network, we can reduce the variance of our updates and have a more stable learning trajectory. To state this another way, what we achieve by having multiple different workers play different episodes with the same parameters, we achieve more stability. This is like, say, instead of doing stochastic gradient descent, where you look at one sample at a time, you can do batch gradient descent, where you look at several samples at a time. As you may recall, this makes the loss per iteration much smoother. This might also remind you of the deep Q network section, because in that case, we also wanted to add different features that helped us stabilize learning. In particular, that involved techniques like freezing the target network and using an experience replay buffer. Using an experience replay buffer allowed us to look at multiple examples during each training step, which is a little bit like batch gradient descent, and so intuitively we understand how this helps us stabilize learning. In short, stabilized learning is good, and we can achieve that by looking at multiple samples at the same time. It just so happens that with A3C, the way that we do this is by having multiple parallel copies of our agent playing the game. This is what allows us to make use of neural networks as our function approximator, whereas they don't work well with vanilla policy gradients without parallelization. In other words, deep Q networks and A3C both try to solve the same problem, which is how can we make use of neural networks in classic reinforcement learning algorithms? They just happen to do it in different ways. In the rest of this lecture, we're going to discuss how the code is going to be structured. Remember that the actual algorithm we'll be using is nothing new. It's just the same old advantage actor critic that we saw before. The difference now is that we want to have concurrent agents that asynchronously copy and update their parameters. So the way the code is structured is this. We're going to have 3 files. The first file is main.py. This is sort of the master file, which is going to be responsible for creating the master global policy network and value network. It's also going to coordinate the workers. In other words, it's going to create a handful of workers, each with their own thread, and then wait for them to complete. The second file is worker.py. As you can tell by the name, this is going to contain all the classes and functions that make up the worker. Each worker is responsible for creating its own version of the policy network and value network, copying the weights from the global networks, playing episodes of the game, and calculating gradients to be sent back to the global network. Finally, the third file is nets.py. This contains the definitions for the policy network and value network. In the next few slides, we'll be looking at the pseudocode for each of these 3 files. Oh, and by the way, you can find these files in the folder A3C. In the first file, main.py, the basic structure is this. First, we're going to instantiate our global policy network and our global value network. Then we're going to count how many CPUs are available and create that many threads with one worker object for each thread. We're also going to create a global thread safe counter that's going to tell us when to quit, since we're going to go up to a maximum number of steps. You'll see exactly how that works in a later lecture. In the second file, worker.py, the basic structure is this. We're going to have the run function, which is going to be run by each thread. The run function just runs a simple loop. First, we copy the parameters from the global network to our local copy of the network. Then we run n steps of the game. At this stage, we store all the data we need to pass into our neural network, such as the states we encountered and the rewards. Then we update the parameters of the global network using the gradients from the last n local steps. To give you an idea of how this might work, we can think of it in terms of these equations. The first step is to calculate the gradient, which is the local cost with respect to the local weights. The second step is to update the global weights using gradient descent with the local gradients. Now, of course, in TensorFlow, it's not going to look exactly like this because we don't actually explicitly write out the gradient descent update. Instead, we'll be using an adaptive training algorithm such as RMSprop, and our actual goal will be to figure out what is the correct TensorFlow function to apply this sort of mixed update where the gradient used to update the weights of one network actually comes from the loss of another network. The worker.py file is probably going to be the most complicated of the three, so you just have to wait and see what the exact details are. Just keep in mind each of the above steps will actually turn out to be multiple functions. The last file we're going to discuss is nets.py. This more or less just implements the policy network and the value network, although there are some important details to talk about before we dive into the code. First, these networks are going to be convolutional neural networks, which means they're going to consist of a series of convolutions followed by a series of fully connected layers. In addition, both networks are going to share a common body. In other words, only the last layer of each neural network is going to be different, and all the preceding layers will have shared weights. Conceptually, you can think of this as a two-headed dragon. I'm not going to go into too much detail now about how this is implemented, but in TensorFlow, we'll want to make use of variable scopes and an argument named reuse, which tells TensorFlow to use the same weights that were already created. In the next few lectures, we'll look at this code in depth.